Today I'm going to talk about my recent work, which is a joint work with my great collaborators, Yang and Jing, and my supervisor, Rupa. So although the title is about memory, but I'm going to start with a simple game. Let's say we have an agent traveling around in this small game. And first, the agent will learn a local policy in this red area. And then it may move to this yellow area where there's a small mouse here. So it has to change its policy to adapt to that. However, there will be a problem. Once the agent learns a local policy in this yellow area, then it may forget its previous learned local policy in this red area, which is a phenomenon called catastrophic forgetting. And to mitigate that problem, we introduced the replay buffer, which is already a standard component in deep reinforcement learning used in model-based reinforcement algorithm and all policy algorithms. And by introducing the replay buffer, we can store all these previous transitions into buffer and transform this non-ID data to ID data so that we can reduce catastrophic forgetting. And also because we already stored these samples, we can sample transitions from this buffer many times and extract as much as information from these experiments to improve sample efficiency. Let's see a concrete example that catastrophic forgetting in single IO tasks. And first, I'll use dequeuing example here. And we test dequeuing in two scenarios. First, dequeuing with large buffer, which has size like buffer size 10,000. And now one is called dequeuing S, which has a very small buffer with size 32. And the mid-dequeuing U is our algorithm I will introduce later, but you can ignore it first. So we can see from these graphs that, from this graph, we can see that dequeuing is okay with using a larger replay buffer. It learns quite stable. However, when we have a really small replay buffer, then dequeuing starts to struggling learning to solve the game, and the learning performance is quite unstable, as we can see the large standard errors here. And let's look into the reason why is that. So we plot the greedy action theory training for these two agents, and in this case, the optimal action is 1 actually, and we can see that dequeuing first struggles to learn the optimal policy, but then it quickly converges to the optimal action, which is 1. However, for dequeuing small, which has a really small replay buffer, it is able to learn the greedy action, learn the optimal action. However, it quickly forgets, and then relearn it, and forget, and relearn. This basically explains why the performance is so unstable and the learning, the sample efficiency is so low. And that's also the reason why we need a larger replay buffer here.
It's a batch size in both the cases?
Sorry?
Batch size of the update.
Batch size 32.
In both the cases?
Yeah.
And this is P4?
P4?
First in, first out?
Yes, right. Okay. By the way, if you have any question, please just let me know. And okay, so we have demonstrated that the forgetting issue does exist even in single IO tasks, where previously researchers mainly focus on multitask continual reinforcement learning. And the forgetting issue is largely masked by using a larger replay buffer. If we use a small replay buffer, it still exists. And without a replay buffer, a single IO task is actually quite similar to a series of IO tasks without clear task boundary, which means to learn a single IO task without a replay buffer actually is much harder than learning a series of IO tasks with clear task boundary sequentially. And this is because we have a non-stationary state distribution, and the policy is changing due to policy update. And finally, it may also because the environment itself is changing, which is quite a challenge. However, using a replay buffer is definitely not an ideal solution. The current usage of replay buffer is not memory efficient. We store raw experiments directly into a buffer. For example, to play Atari with dequeuing, we need to store 1 million transitions, which takes about 7 gigabytes to store them. And this limits the application of the reinforcement learning algorithm to onboard and edge devices, because these devices have a very low memory quota. And next, we humans do not store or save row experiment directly. We save something else. We compress them. And finally, we can save everything in a buffer, especially in a changing world, because the memory is limited by the agent's hardware. That is not easy to change. However, the environment itself may generate infinite many observations. It's simply impossible to store them all. So what's the solution then? Well, in this call, we say that saving information in neural networks is more memory efficient, and here's the reason. So in DeepIO, agent usually save information in the replay buffer. For example, the transition, all these experiments are in the replay buffer. Or we can store them in neural networks. For example, we store policy pi, value functions v and q in the form of neural networks. And neural networks are actually compressors. We can compress all these row experiments into a compact functions like pi, v, and q. And saving information in neural networks is more memory efficient, but there's one problem. Neural networks, as I demonstrated previously, is very easy to forget. So the problem is here, we need to address this problem without using a large replay buffer. By reducing catastrophic of neural networks, I mean, we need to balance between remembering old knowledge and learning new knowledge during IO training, which is kind of like a hard task. Again, I'll use a deep learning example. So I'm sure, I guess people here are already familiar with DQ, so I won't dive into the details. But first, notice that in DQ, we have a target neural network, Q hat, which is originally introduced to stabilize training. And for every C steps here, we will reset Q hat to BQ, which means in most cases, in most training steps, Q hat is actually an old copy of Q, which means it stores old knowledge. And where does this new knowledge coming from? It's coming from new transitions, where the agent is interacting with the environment. So the natural question is, how can we combine the knowledge from these two sources to avoid forgetting and also learning new knowledge? So finally, we are introduce our method. Basically, we are introduce a new training loss, and it has two parts. The first part is the traditional DQ loss, and we use them to learn new knowledge. And the second part I call the knowledge consolidation loss. It's used to keep old knowledge. And the intuition here is that we want to keep Q and Q hat close to each other so that we can maintain as much as old knowledge. And here we only care about states sampled from this stationary distribution, because that's all we care about. And you also notice that there's some lambda here, which is you introduced to balance between learning and consolidation. Because in reverse learning, we not only need to remember old knowledge. Whenever we have like new information, we also want to update them. And this is the role of lambda here. So finally, notice that as a sample from the state distribution dpi here. However, we don't have an analytic expression of dpi. So the problem is, how can we get the stationary state distribution dpi here?
Can you quickly explain L consolid again?
So
can you explain the new loss again?
Okay, sure. So as I previously mentioned, that Q hat is basically a knowledge base for all knowledge. And during update, we want to absorb new knowledge by using this DQ loss, but we also keep the old knowledge by push Q towards Q hat so that their function values are close.
I see. And what is fixed here and what is changing? So theta minus is fixed, like theta is changing.
Yeah, right. We optimize theta, not theta minus. Theta minus is fixed.
Instead of the hard update, is Q equal to Q hat old or Q equal to Q old, you do this.
Yeah. Oh, you mean how do we update Q hat?
How do you update Q hat?
Oh, we still update them like every C step, and we copy Q to Q hat. So for example, if we set lambda to 0, this will be exactly like DQN. The only difference is we add another loss here. Any other questions?
Like a trust region,
Sorry?
like a
It's kind of,
proximal thing.
yeah.
Trying not to move too far away from Q hat.
Yeah, it's similar. Actually, trust region, they have close relationship, and I would say that trust region is actually a special method of knowledge consolidation.
I see.
Okay, I'll continue. So the question is how to get the stationary state distribution d pi. So the first method we introduced called uniform state sampling, and the basic idea is to approximate the state distribution with a uniform distribution on the state space S. And because sometimes we don't know the state space ahead, so here I will approximate the state space with the interval S low and S high. S low and high are the bounds of the state space. And this is the pseudocode of memory sharing DQN with uniform sampling. And notice that there's only small difference. So first here, we initialize a small replay buffer here, which means, for example, we only have a buffer size 1 mini batch. And we also initialize state bounds S low and S high so that they are the upper bound and lower bound and upper bound of the state space respectively. And whenever the agent receives a new state, it updates the lower bound and upper bound so that they will always be the bounds of all previous seen states so that they can be a compact approximation of the state space. And during training, we compute the DQN loss, and we then sample 1 mini batch state uniformly from this interval. And we then compute the logic consolidation loss. And here, the logic consolidation loss is a little bit different. Yes, question?
What is S low and S high? Can you explain that?
So let's say original, there's no state we've seen. And then the agency one state, we want to all the previous states to be included in this interval. And that's why we introduced the this S low and S high bounds. So that whenever we introduce a new state, if they are already in the bound, then we don't need to update this bound. However, if they are outside the bounds, we update them to include the new state.
And the size of S low is the size of?
Yeah, good question. So the dimension of S low and S high is the same as one state in the state space. For example, if we have a state space with dimension 10, then S low and S high are vectors with dimension 10. Okay. So let's get back. So the consolidation loss with uniform sampling looks like this. And the only difference is here that we no longer sample state from the d pi here. We sample it from a uniform distribution from the state space S. And in practice, we sample it from this interval. And after we compute the logic consolidation loss, we combine them together and do a gradient step. And theoretically, if we assume the size of the state space is finite, we can prove that the original consolidation loss is actually upbounded by the term that is the product of the size of state space and the consolidation loss with uniform sampling. And this means if we can minimize the consolidation loss with uniform sampling to a small value, we can also minimize the upper bound of consolidation loss. And due to the generalization of neural networks, even with pseudo states, we can achieve good logic consolidation in some cases. This means we don't really need real states. Even pseudo states can work here. And we call this new algorithm a DQN U. Okay, great. Any other questions here? Okay. So let's look at to verify that DQN U can really reduce casual forgetting here. And here there are 3 agents. We test DQN with a large buffer, DQN S with a small buffer, and DQN U with a small buffer, which also has a size 32. And you have seen previous 2 figures here. So I just focus on the last one, which is the DQN one. And we can see that without a large buffer, DQN S here keeps forgetting and relearning optimal action. However, for mid-deacon U, it suffers much less from forgetting, although it uses a very tiny buffer. Yes.
Could you explain which part you show this is memory efficient? Could you explain again? I'm still.
Oh, okay. So by memory efficient, I mean we can use a much smaller replay buffer. So for example, here Deacon use a buffer size 10K, and we use buffer size 32.
Oh. And second question is, could you explain the phenomenon? It appears in the first figure that Y at step 8,000, if there's a drop on the grid action.
Okay, so yeah, good question. So I personally think that is that because it still has forgetting, it's just won't forget much that much. So by introducing a rebuffer, we can mitigate the forgetting, but we cannot remove forgetting totally.
What is this plot? What's on the y-axis? It's saying that I take the greedy action, go right all the time.
Yeah.
That wouldn't work in mountain car.
Oh, this is the greedy action for one specific state, not for all states.
It's on different steps.
Yeah, iterative training. Yeah, exactly.
What does this show?
Sorry?
What can I
Okay.
on this plot?
So you can see that for DQN, it quickly converges to optimal action.
We know that one is optimal in this state.
Yeah, yes, that's right. So which is a good phenomenon because we want to converge to optimal action here. But for DQNS, the grid action changes constantly, which is not good because that will reduce performance.
I'm sure you have tested this, but an action, if it's optimal in a certain state, it is also dependent on what other actions I take in other states. So maybe it's oscillating, the whole policy still remains optimal.
That's possible, but in the end, the agent will converge to one optimal policy if, like with enough assumptions, right?
You showed in the first slide that it was like much worse than.
So along with that and this figure, then we can say this should probably be going to, okay, makes sense, thanks.
I'll show that part later. Okay. Shivansh, yeah.
How are you training the deacon, like using alleviate or something?
Yes. Any other questions? No? Okay, cool. Let's continue. So next topic is about balancing between learning and remembering. And previously mentioned that Lambda can be used to do that. And here we'll run experiment to verify that. And so first, for a small fixed Lambda here, let's say in extreme case, Lambda is 0, then will there only be deacon loss, which means we want to encourage learning new knowledge. And for example, when Lambda is 0.01, the red curve here, it learns fast initially, but then it becomes slow and unstable later. So which is bad. And for fixed large Lambda, then in this final tuning loss, then the consolidation loss will dominate, which means we want to encourage keeping old knowledge. And let's say Lambda is 8 here, it learns slow. The learning is quite slow initially, but the final performance is quite stable. So these two phenomena points out a good strategy that is just linearly increase Lambda so that learning can be fast and stable. As we see here, by increasing Lambda from 0.01 to 4, we can achieve fast learning initially and good performance, and good and stable performance in the end. And since this strategy is so useful, we will keep using them in the following experiments. So that's the part Shivan care about. We then evaluate all these algorithms in low dimensional tasks. By low dimensional task, I mean the dimension of the state space is quite low. And again, we have 3 agents: DQN with larger buffer, DQN S with small buffer, DQN U with small buffer. And we test them into 4 environments: mountain car, aircraft bar, catcher, and Pixcopter. And the number here in the parameters is the number of dimensions for the state space. For example, for mountain car, the state space has dimension 2. And all these dimensions are quite small, below 10. And we can see that mid-DQN performs well which is the blue one. It achieves comparable or even better performance compared to DQN. Note that median U here only has a buffer size 32, while DQN has a buffer size 10,000. Yet we can still achieve comparable, even better performance.
Why is that? That's magic.
Because it reduces forgetting. So we introduce a large buffer to reduce forget. And here, media can use logic consolidation to reduce forgetting so that we can avoid using a large buffer.
Bias from data correlation doesn't matter.
It doesn't matter, but we reduce the negative side of the related data. And media can use, as I said, is more memory efficient. And basically, we can say that in low dimensional tasks, the replay buffer can almost be fully removed without hurting the performance if we use median U here. Okay. Next, however, there is still a problem with this uniform state sampling. And remember that in uniform state sampling, we approximate d pi with a uniform distribution on the state space S. However, as previously introduced by Horan, the big word hypothesis, which is that we usually have a super large state space. And in this big world, the agent simply can only visit a small subset of the states in the state space. In this case, a uniform distribution over S is far from a good estimation of d pi. And theoretically, in this case, because the size of the state space is so large, this upper bound will no longer be a good upper bound. So what's the solution? So the solution here is we just approximate d pi by sampling real visited states, because these real visited states are more close to the states induced by this policy pi. And this new method, we call it real state sampling. And the basic idea is to approximate the state space with a set of real states here. And compared to median U, it still has a relatively large buffer. And when we do updates, we sample 1 mini batch states from this replay buffer and compute this new consolidation loss. And this consolidation loss is simply by sampling states from this buffer. That's the only difference here. And we call this algorithm median R, memory efficient DQN with real state sampling. And although it uses a relatively large buffer, but as we are shown next, it's still much more memory efficient than DQN. So we validate this algorithm in mini Atari games developed by Kenny, which is basically a mini version of Atari games. We have 4 agents, DQN with buffer size 100K, DQN S and median U have buffer size 32. And finally, median R has a buffer size 10K, which basically is 10 times smaller than the buffer size used in DQN. And here are the results. There are 4 games. And again, the number in the parameters is the number of the dimension for the state space in each environment. And we can see that in terms of performance, basically we can see that median R in the green curve is slightly better or comparable to DQN, which is shown in the red curve. And DQN is better than median U in some cases. And finally, median U is significantly better than DQN S. So we can see that median R is more memory efficient than DQN, while achieving comparable or even better performance. And median U performs much better in low dimensional tasks such as asterisks and breakout. They only have dimension 400. However, it performs worse in high dimensional tasks such as space invaders and sequence. So this is the reason, because we mentioned that previously, for high dimensional tasks, uniform state sampling is no longer a good approximation of the state distribution d pi. And we verified that in these experiments. Okay, next we want to confirm this further. So we evaluate them in Atari games. And in this case, we have 3 agents. DQN in the red, shown in the red, has buffer size 1 million, which is about 7 gigabytes to store them. And another DQ has a buffer size 100K, and our algorithm DQ has a buffer size 100K as well. And for these last two agents, it only takes about 1.7 gigabytes to store the repeat buffer. And in all this game, the state dimension is about 7,000. And these are the results. And showing the blue curve mid-DQR. And we can see that it can reduce the memory usage of repeat buffer from 7 gigabytes to 0.7 gigabytes without hurting performance or even improve them. For example, in nameless game, our algorithm actually performs much better, and in Qbert and in these two algorithms, in these two tests actually is slightly better. And yeah, the other two algorithms, it's comparable DQ with a large buffer and much better than DQ with smaller buffer.
Forgot. There was QSA, S was coming from DPy. Where was A coming from?
Sorry?
In consolidation loss. You don't have to go back.
Yeah.
Yeah. Where is A coming from? This is.
You mean action?
Oh, you sum it overall.
Yeah, because this is like a discrete action space. We can summarize all of them.
Sum it? Why not use the policy to weight it or something? Closer to DPy.
Because we want them to have a good approximation for across all action values uniformly. That's
in all the states.
Sorry, not in all states, in the sample states. I've tried that using a policy like epsilon greedy, but it's actually not that helpful. Okay, any other questions?
What were the hyperparameters in the last experiment? So it's like the default equivalent parameters.
Yes, right. But there are some other hyperparameters in our own algorithm that we tune a little bit, but it's very small scope.
equivalent is also pretty good here. What if we go even lower? Maybe it's coming on the next. What if we have a buffer size of 10K or 50K?
Oh, I actually haven't tried that. I guess the result will be much worse. It's already worse. For example, in nameless game, we can see a clear separation here. And in battle zones, in some cases, because I guess, for example, for double dunk, the forgetting issues is actually not the bottleneck. Maybe there's some other problems, for example, exploration, something like that. So that's why the performance gap is not so clear.
And that is again on the linear schedule.
Yeah. Oh, there's a question in the chat. The question is in slide 16, what is the performance of DQN with the buffer size 10K? And how do you set the hyperparameters of these methods? Are you using the same for all methods? With 10K. Oh, so I didn't show here, but there's some results for mid-DQN in Sequest that we test a series size of buffer sizes, and in that case, mid-DQN is still better than DQN. And for the second question, are you using the same hyperparameter? Yes, for common hyperparameters, we use the default one. But for mid-DQN, there are some special hyperparameters, for example, the lambda here, and also we update for example, we do multiple updates here by tuning E here. But in Atari, actually, we found that E equal to 1 is better. So actually, the only difference is the lambda here. And we also tune a little bit about the target network update frequency. And you can list all the parameters in our paper. You can check that.
Is it sensitive?
It's a little bit sensitive, but we can get a very intuitive scope. I only test like two hyperparameters. Cool. So next, previously I showed you that mid-DQN is more memory efficient, and actually it's more computation efficient. And here's a table of the training steps, training speed of two algorithms in 5 games. And for example, in Battle Zone, DQ training speed is about like 230 steps per second. For MeetDQU, the speed is 330 steps per second. And why is that? Because it reduces forgetting, so that we don't need to relearn again, which means we can reduce the number of updates to save some computation. Okay, so to conclude, the take-home messages are: first, without using large buffer, catastrophic forgetting exists even in single I/O tasks. And by reducing forgetting, we could improve memory efficiency, sample efficiency, and computational efficiency. And we should our algorithms are more memory efficient. We are achieving a similar or even higher performance compared to the baselines. And finally, for high dimensional tasks, we recommend MeetDQR. And for low dimensional tasks, when the memory is very limited, we recommend memory efficient with uniform state sampling. That's all from me today. Thank you. And we're having this meeting.
Your consolidation loss for maybe the catastrophic value problem, does it work for other problems? For example, supervised learning has different domains, and I can do the same thing like the prediction probabilities. I can penalize the difference of the change. Does it work for traditional value?
I didn't test in large scale, but in our paper we do have like a small scale testing to approximate a sign function, and we show that it actually helps. Yeah, but this idea, knowledge consolidation or knowledge distillation, is actually quite an old idea. It's widely used in many areas.
Knowledge distillation is the same as knowledge consolidation?
Actually, I would say consolidation is a special case of distillation. By consolidation, I mean we consolidate what is already inside the neural network to itself. But for distillation, it's more widely. For example, we can transfer knowledge between two neural networks with completely different neural network structures.
Okay, then another question is, since Q's are distributions, why do you apply mean square errors on Q?
Yeah, that's a good question. We can also, I didn't try a lot of options, but we can also apply, for example, KO divergence to constrain them.
Divergence.
Oh, sorry, I didn't attend that talk, sorry. But I guess, yeah, this is actually an open problem. We don't have like a theoretical result to say that what's the best form of this knowledge consolidation. It's more like related to offline I/O problem. We have larger buffer. We want to learn a good policy, recover a good policy from this buffer.
The Q is a distribution.
No, it's a value. Okay, sorry.
Yeah, I get the idea. Okay.
Why did you use dpi?
Sorry.
I'm asking too many questions. Why did you use dpi in the weighting for states?
D pi?
Stationary state distribution.
Oh, sorry. What do you mean? What are the other options?
Say uniform or from my buffer.
Oh, this is because we don't need to care about this d pi, right? Because that's we all need to know for other states, if they are not visited, why do we care about?
These are episodic tasks. Do they have dpis?
Yes, if you like visit them many times, in the end they are converged to a positive pi.
In the end, isn't it all like game end?
Yeah. I mean, is that?
It's not dpi. It's not stationary state distribution. Actually, I don't know what stationary state distribution. What is stationary state distribution?
So for any positive pi, there's induced state distribution, right? If you visit, that's the integral cases.
Isn't that in the continuum case?
I think in both cases. Sorry, there's the. Oh, sorry. Share screen again. So another question from Hongming. Since the goal is to use a small buffer, how about methods that do not use repeat buffer, such as actor critic and PPO? Well, these methods have the problem for getting with them perform worse than this proposed method. Okay, that's a good question. So my answer is that there is a small buffer in PPO. So if you look at the implementation, there is a small buffer. And if you reduce that buffer, the size of that buffer, I guess the performance will also be worse. I hope I answer your questions. Next, what do you think if we tune hyperparameter each method individually? Is it possible to get a different conclusion? Is it possible that DQN with its best hyperparameter can perform better than your algorithm with its best hyperparameters? Yes, we actually do that in our paper, but only in one specific task in Sequest. And the result we showed is that the knowledge consolidation helps. It's not because we tune more hyperparameters. It helps because it reduces forgetting. Okay. Any other questions?
This is quite interesting, right? This simple loss and it.
Yeah, and also
by forgetting over this complex landscape of state and actions.
Sorry.
Like there's this super complex landscape of state and actions, and there's this simple loss for this.
Yeah, it helps, but so you'll notice that I still use a large buffer in sorry. I still use a large buffer to play Atari. So we cannot reduce catastrophic getting to extend that we don't need a large buffer. So it's still a hard problem, and we are still working on it. Actually, there are not many papers about this case. People are all concentrating on multitask continuous learning, but actually we haven't really solved the continuous learning problem in single IO task by when there's no large bigger buffers.
Can this also help there?
Have a what?
Multitask continuous learning.
Yeah, there's actually a similar idea that used to reduce forgetting in multitask continuous learning. But however, when they learn a single task, they still use a large buffer.
What happens if I have a large buffer with me, DQ, and R? 1 million.
So actually the best replay buffer is we need to tune that to find the best replay, the size of a replay, because when you have a too large buffer, you'll add too many off policy data to it, which is bad. So if we use like a really large buffer with medium, I guess the same problem exists as well.
But would it be better than DQ? And like, should the consolidation loss be the default when I train an agent?
I guess, yeah. All right, we do test that. When, for example, in Sequest, we test medium R with buffer size 100K. It's still better than DQ, but actually it's slightly worse than buffer size 10K because the buffer size is too large, and there's too many out policy data in it.
So DQ and 10K will perform better.
And I mean, medium R with buffer size 10K is better than medium R with buffer size 100K.
Would the same results be valid for then DQ and 10K?
So in all these cases, medium R is better than DQ with different buffer sizes. Yes. Another question. When do you observe when you increase or decrease the buffer size on medium U and medium R from 32 to 10K respectively? So we do test medium R in Sequest with different buffer sizes, and we can observe, similar to DQ, we can observe optimal buffer size as well. And for DQ medium U, we didn't do the experiments, but I guess the results is quite similar because this is the problem of DQ algorithm, not the problem of consolidation loss. There is a best, there is an optimal buffer size if we tune enough parameters. Yes.
The graph of buffer size to performance, is it like an upside down view?
Okay, maybe I can just show you the paper. 1 second. Okay, can you see the screen now? So in table 2, we test 2 algorithms with different buffer sizes, and you can see that mid-DQN are in all cases outperform DQN. However, there is a optimum buffer size which is around 10,000, and when you increase it, the performance actually slightly drops. And similar for DQN, there's an optimal buffer size. Yes.
Can you go back to the slide with the loss function for consolidation and so this part, your new consolidation loss is a sum of state and action computing the differences between two Q functions.
Yes.
So what if there is a dominant differences? For example, one of the state action has never been explored or explored rarely, so the Q value is infinite or something like that. That's dominate the full loss.
Well,
Actually, we all have the same Q, but for one, we have a large index.
so if the magnitude of Q value actually matters a lot, then we can probably use something else. For example, we can regularize the policy instead. We can use KO divergence to regularize the policy induced by Q with the policy induced by Q hat. So in that case, magnitude doesn't matter a lot, I guess.
Yeah, for most of these algorithms for there is all of those, they will have an issue of string values. So we have a predicting method to just make sure that for each of the values we just can know that they are in a safe bound or something.
Yeah, that's a very good idea. I think maybe we can also normalize it, something like that.
And another question is that for it seems for me like the magnitude of the L, DQ, and L consolidations not necessarily the same, right? It makes it hard to understand what lambda would be to make sure that we have a perfect balance between L, DQ, and L consolidation. So, for example, in different experiments, we might need to test out what would be the lambda value of 0.1 meters in different experiments, probably in different settings. We have different magnitude of LDQ and L consolidated. We need to again rebalance the values by twisting the lambda.
Oh, you mean tune lambda based on the, for example, difference?
So, for example, I have a new task that's never been used by any study, so I'm not sure what would be a perfect value for lambda. So what would 0.1 lambda means in my new experiment, and what would be 1 means, and what would be 10 means. I need to test it out, right?
Fine, I see your point. So that's a very good idea. We can actually use meta learning, I guess, or similar method to tune it automatically. Yes. But I don't know whether it's hard or not to do that, but yes, it's a good idea. Any other questions?
Seems such a simple idea and works so well. Why did people try it before?
Well, so first, most people are focusing on multi-line continuum algorithms, and they already applied. But in single task, they didn't pay much attention to that. Yeah, and for example, in UA, people like continuum learning problems, and in continuum learning problems, there's just one task with changing distributions, and yeah, we can bring like many ideas from other related work and apply here. It's quite simple and quite effective. And as I pointed out, by reducing forgetting, we can achieve, we can improve memory efficiency, sample efficiency, and computation efficiency, which is quite beneficial. And we should keep doing that.
Does this also reduce the, finally, I just care about the wall clock time, right? It also reduces that.
Yeah, yes, as shown in the table, the training speed for mid-DQN is much higher than the training speed of DQN. The training, for example, in this environment, the training, for each second, mid-DQN can be trained with like about 300 steps. But for DQN, we only trained with about around 200 steps per second. So the actual training workload time is shorter. Okay, if there's no more question, then thank you for joining our talk.